Hello, welcome to a lecture on formal specification and verification. My name is Dr. Velayat Khan. I'm an assistant professor at Comstate University, Islamabad campus. In this lecture, I'm going to formally specify and reason about natural numbers and in particular net list. So far, we have developed Coq script based on the book software foundations. These two libraries, basics and induction, that we have been completed in, they have been compiled using the Coq compiler, and after compilation they have been included here using the require import command. So basics is the library, induction is the library, and then in this library list.v we have defined net product, net list, which is a list of natural numbers, and many functions and notations for the net list. And at the end we stated and proved a number of lemmas and theorems. In this lecture I will just continue from that point onward. Okay, so our next lemma, our theorem is lemma non-zeros fn for all L1, L2. We have non-zeros. So non-zero is basically a function that remove zero members from a list. So if we concatenate two lists, L1 and L2, and then we remove non-zeros, the zero elements from these lists, and the non-zero function would just return a list of non-zero elements. So this applying non-zero function to concatenation or append of L1 plus L2. So we just concatenate or append L1 with L2, and then we apply non-zeros function to the appended version of the two lists. This is equivalent to applying non-zeros to L1 and then concatenate with append it with non-zeros L2, and I will just enclose these two in the parenthesis. Okay, so what is the statement of this non-zeros append lemma is that L1 and L2 are appended with each other, and the non-zero operation function is applied to it, and this is equivalent to applying non-zero, parenthesis is misplaced, applying non-zeros separately and then appending the resultant lists. Okay, so let me compile the statement of this lemma. This is okay. So we can now enter into the proof mode. Here, and we continue as usual with introducing the variables above the line. Okay, so L1 and L2, the two variables have been introduced above the line into the hypothesis, and then okay, case analysis. We use case analysis using induction tactic. Induction L1. So L1 as a list. So as we can see here, so induction on L would give us two sub goals, and one L1 would be null, and in the other L1 would be non-null list. So let me compile this. So we have now two sub goals, and the first sub goal L1 is null, and in the second sub goal L1 is non-null. So using the plus operator, I will just focus on the first sub goal, and with this the second sub goal would disappear for the time being. So here in the first sub goal we have non-zeros. Null appended with L2 is equal to non-zeros of null, and this is appended with non-zeros of L2. Okay, so simplification is the tactic that we should try now. After we simplify, we get this would be reduced to just L2 because that is what append function is defined. And non-zero, when the list is null, it would just return null, and again the first argument is null, so this fn operation function will return the second argument. So in both cases we get non-zeros L2, non-zeros L2, so we can close this with R2. Okay, so we have a second sub-goal, unfocused sub-goal. To focus on this sub-goal we use the plus operator. Okay, so here we have okay, so let me we cannot apply the inductive hypothesis that we have in the hypothesis, nor we have a lemma or theorem that we can rewrite here at this stage. So let me try simplification and we can see what happens with the sub-goal. So okay, after simplification we get to this situation where we have if then else statement. If n is equal to 0, this is Boolean operator, then non-zero return and then this function will return this non-zero L1 appended with L2, else this. So we can still continue with case analysis, and in this case this operator is equality, Boolean equality, so we can use destruct on this equality. So when we destruct this equality, we would get two sub-goals. In one sub-goal the then part would be followed, while in the other sub-goal the else part would be followed. So let me destruct equality B. Okay, so we got two sub-goals, and the first, to focus on the first sub-goal, I use the minus operator, and here okay, so now we can rewrite the inductive hypothesis, because here non-zeros L1 plus L2, non-zeros L1 plus L2, so we can rewrite the inductive hypothesis 1. So what this inductive hypothesis does is that this part, this term is exactly in the goal. So when we rewrite this inductive hypothesis, this is rewriting from left to right, so the left part of this equality is searched or found in this sub-goal, and it is replaced with the right part. So this expression or this term is replaced with this. So that's what we can see after we compile this rewrite operation. So okay, so now we got both the left hand side and right hand side are exactly the same. So we can close this sub goal as well, and we can now focus on the second part of the second goal. Okay, so again we cannot apply the inductive hypothesis in the hypothesis about the line. If we simplify it, and then we see if we can, it can be useful. Even in this case we can write the inductive hypothesis, but that not would give us left hand side and right hand side equal. We can write this expression with this. Okay, but if we simplify it, this will not give us what we need, because this the parenthesis would create problems. So let me simplify it first. Okay, so after simplification we introduce the parenthesis. Okay, so if we simplify it, okay, so now if we rewrite the inductive hypothesis, probably would be we would get the goals where the left hand side and the right hand side would be the same. So let me rewrite the inductive hypothesis L1. Okay, so this is what we need. Left hand side and right hand side are the same, so we can close this goal with R2, and we are done with this lemma. Okay, so this was one way to prove this goal, but this theorem like this can be closed using the assert command as well. So let me introduce a new lemma with the same lemma with a new name, zeros underscore fn prime for all L1 and L2 non-zeros L1 plus L2 is equal to non-zeros, L1 plus non-zeros L2. Okay, so it is the same lemma, but I want to instead of using case analysis on the equality B destruct, sometime it is difficult to find the exact name or to tell the Coq to destruct that operator. Then in that case we can use assert command to introduce the equality or an additional hypothesis, and then we can use a rewrite tactic to do the case analysis. So let me show you this with the example here. Okay, so entros, we enter into the proof mode and then we entro, so all the variables go into the hypothesis. And okay, so tell that destruct, I continue as usual. So induction on L1, the steps till here are exactly the same, so I will just proceed with the same way. So induction on L1, induction, sorry. And when I use induction on L1, we get two sub-goals. In the first sub-goal, we use simplification, and we would be able to close this goal with R2. And in the second sub-goal, use simplification to introduce the equality, the add the null statement. Okay, so at this point, we have the equality on n and 0, so n is equal to 0. This is Boolean equality. So instead of destructing this equality Boolean, I introduced or assert. So I assert a statement that n Boolean equality 0 is equal to true or n equality Boolean equality is equal to 0 is equal to false as equality hypothesis equality B. So I introduce this is the equality on n and 0. So this can be true, this can be false. So I introduced a hypothesis that n is equal to 0 is true or it is false. So either of these two is true. So I assert hypothesis, and this appears here as a sub-goal. So then after this I proceed with the proof of this hypothesis or this sub-goal, and for this we can use either minus or we can use curly brackets to separate the proof script of this introduced or asserted sub-goal. So we destruct or use case analysis on n. Two sub-goals for this asserted lemma or asserted hypothesis. So we have disjunction. So we can use left command to choose the left side, because we see that 0 is equal to 0 is true, and we cannot choose this 0 is equal to 0 false, because this is we cannot prove this, but we can prove the left part of the disjunction. 0 is equal to 0 is equal to true, so we use the left tactic to choose the left side, and then we can simplify it. So simplification would give us true is equal to true, and that would give us we can close this with R2. And similarly, the second goal, the second sub-goal of this asserted hypothesis, we can choose the right part of the R operator. So S of n is equal to 0, this is false, and S of n is equal to 0 is equal to true. We cannot prove this, but we can prove the right part, so that's why we choose the right part of the disjunction. And we again simplify it, and we close this with R2. And okay, so this proof is completed, and when I close this proof, we will see a hypothesis here, a hypothesis equality B, which is the name we have given to it, and the statement or the definition of this hypothesis here that is what we desired, and we have the same hypothesis here. So we have introduced a hypothesis here. Okay, so now as we have a hypothesis, we can now destruct this hypothesis. Destruct, because there is a disjunction, so we would get two sub-goals. For one sub-goal we would have n is equal to 0 is equal to true, and in the other sub-goal we would have n is equal to 0 is equal to false. So destruct equality, hypothesis equality B, we would get two sub-goals here, two sub-goals. Okay, in the first sub-goal, the left part is given, while in the second sub-goal the right part is given, which would reappear after we focus on the second sub-goal. Okay, so to focus on this sub-goal, use the minus sign, and I just rewrite the inductive hypothesis H, that is the new hypothesis here after we destroyed the hypothesis on equality Boolean. So we rewrite it here. So n is equal to 0 is true, so this expression would be replaced with true, and it would automatically be reduced to non-zeros L1 plus L2, and similarly here n is equal to 0 would be replaced with true, so we would get n non-zeros L1. Okay, so let me rewrite it. Okay, so after rewriting it, we got non-zeros L1 plus L2 from the left side of the equality, and we got non-zeros of L1 plus non-zeros of L2 on the right side of the equality. And this is and here we can use the inductive hypothesis now. So just rewrite inductive hypothesis L1. This is the inductive hypothesis, and we should be able to close this with auto. So we can now close this with auto. Similarly, the second sub-goal, where in the hypothesis we had the right part of the disjunction n is equal to 0 is equal to false. Okay, so we can rewrite this hypothesis H here in all the occurrences where n is equal to 0. So n is equal to 0 is replaced with false. So the else part is chosen, where n, this would be the left hand side of this equality, and else n appended with non-zeros L1 concatenated with non-zeros L2 would be the right part of this equality. So after rewriting H, you would get this expression. And in this sub-goal, okay, we can again rewrite the inductive hypothesis IHL1, and we get the left hand side and right hand side exactly the same, so we can close this with QED. Okay, so these two lemmas are exactly the same, but their proofs are different. So here we use destruct equality B. This proof is simpler and more refined, but this proof is a bit complicated, but we used assert command to assert a proof within a proof, and then use that proof as a hypothesis to rewrite it inside the sub-goal, and then using the inductive hypothesis we were able to close this lemma. Okay, so both proofs are correct, but there are two different ways to prove the same lemma. Okay, so let me define a function to prove or to define equality on two net list. So fix find equality, Boolean equality on lists, two net list, and this function would get two list L1 and L2 of type net list, and this would return bool, which would be either true or false. So here in this definition, as usual, we can either pattern match on one list, or we can on one argument, or we can pattern match on the two arguments at the same time. Normally pattern matching on the two arguments of the function, recursive function, is normally more sophisticated way. The function would be short, So let me pattern match L1 L2 with, so L1 and L2 are the two arguments of this equality Boolean list function, and here okay, so the for the two lists, each list is each list can either be a null or can be non-null. So 4 possibilities are there. So if both lists are null, then obviously they're equal. So we return true if the first list is null while the other is non-null. So for this we use the placeholder. So the first is null, the first list is null, and the second list is non-null. This placeholder actually replaces the two possibilities, whether this L2 is null or L2 is non-null, but the possibility that both of the list are null is exhausted here. So this would be the case where the first list is a null but the second list is a non-null. So in this case it should return false. Okay, and the first is null or non-null while the second is null. It should also return false. Again, in this case this placeholder replaces the two cases where L1 is null and L1 is non-null, but L1 is null is exhausted here, and L2 is null. This situation is exhausted here and it would reduce to true. That's why this case is used first, but here the non-null case is reduced to here, and this would give us false because L1 is non-null, it has some elements, while L2 is null, so they cannot be equal. So that's why we return false from here. Similarly, when both of the lists are non-null and L1 has H on the head of the list and it has some tail, and similarly list 2 has some head prime and it has some tail prime, then in this case we should look for equality on the two values at head of the two lists. So we see if equality boolean H and H prime are same, and then we use AND operator. We just combine the comparison, boolean comparison of all the corresponding elements of the two lists, and we continue this, and we recursively call equality boolean list function on the tail and tail prime, and this continues until all the elements are compared with each other. Okay, and we then end this pattern matching, and let me check. Okay, so syntax of this function is at least correct, and we can now test this function. Would it produce the correct result? So equality boolean list, and we provide a list. Let's suppose 4 4 5 4 3 2 1 is the first list, and we have the second list as 4 5 3 2 1. So these two lists are obviously not equal because the corresponding elements or members are not equal, so that's why it returned false. The first element is 5 while the first element is 4, so these two elements are not the same, and similarly the second elements are also different, so that's why these lists are different. So this is equality, boolean equality on list when two lists are equal, when they have the same size and they have the corresponding elements are the same, and both of the lists the corresponding elements are the same, then the two lists can be considered as equal. So this is what we have defined. Okay, similarly we can define a search function finding an element, net element in list of net. So there is list find function, fixed find, it's a recursive function, list find. This list find function takes an element of net data type, and also it takes a list of net list, and whether or not it returns whether or not the value that we are looking for n in the list L is there or not there. So it would return a Boolean value, and this function is defined to be as okay, pattern matching. We have just one list, so pattern matching on single argument, match L with, and here we have the two cases. So the first case is either the list is null. So if the list is null, then obviously this value n is not in this list, so it should return false. And if the list is non-null, for example, it has a head and it has a tail, then we should look for n and compare it with the head, and if it is equal, then obviously n is there and should return true. And if it is not equal to head, then we should search the rest of list for n. So let me compare this match equality bhn. So what we do is we compare this argument with the head. That's why we use equality boolean head n. Head is the first element of the list and n is the argument that was provided here with. So it would give us two values. Equality bhn would give us two values. In case of true, so again pattern matching, in case of true, it should return true. If h is equal to n, then this function should return true because n is there. And if it returns false, then list find should be again called, and n should be passed as the argument, and the rest of the list should be passed as the second argument. So look for search this n in the rest of list, and this pattern matching is ended. This external pattern matching match is also ended, and the whole function is ended with dot operator. Let me compile this function. Syntax of this function is okay. Now we can test this function. Compute list find 4 5. Okay, so obviously this 4 is in the list, so it should return true. Yes, it returned true, and if I replace this 5 with 6, then 4 is not in the list, so it should return false. Yes, it returns false. So at least in these two tests, we are on the right track. Similarly, we can define a function that would give us if the two lists are equal, regardless of the order of the elements. So for example, Boolean equality on list was defined, and according to this definition, two lists stand equal if the corresponding elements are the same. But now we define another function where the two lists would be equal if the elements of the first list, if all the elements of the first list are included in the second list. So that is a kind of subset of a list. So for example, we can define a function to find if list L1 is a subset of list L2. Text point equality boolean list n prime, because we are going to define another function, so that's why a similar function, a slightly different function, so that's why I renamed this with prime. So it gets two list L1 and L2 net list, and it returns bool. So this list actually look if all the elements of list 1 are included in list L2. If it is so, then it will return true, otherwise it will return false. Okay, so match L1 with L1 and L2 with, so 4 possibilities. Okay, so null, it should return true because null list is a subset of the null, so true is returned. And if first is null and the second is not known, if it is null or non-null, then it should return true as well. It returns true as well. So actually, even if we remove this first line, is this possibility is also included in this line, because this spaceholder replaces the possibility of null as well as non-null, and for both of these we want to return true. So the line highlighted is not required, it is redundant, so that's why I remove it. Okay, so for the other possibilities where we do not know the first argument, if it is null or non-null, while the second is null, then it should return false, because we know that the second argument is null. So if the first argument is null, then this would be covered here and would be exhausted here, and it would return true. But the non-null case would be reduced here, and it should return false, because non-null list cannot be a subset of the null. And similarly for other possibilities where L1 is has the form H with a head and a tail, and L2 is either null or non-null, then in this case let's find H and L2. First look this H and L2, and if it is there, combine it with equality B. Look, compare the rest of list the tail, which is the rest of list L1, with L2. So equality B, list N prime tail and L2, and this is ended with N dot. So what we are trying to define here, we are actually looking if L1, let me comment this out, if L1 is a subset or sublist, better I use sublist of L2, and this function is not comparing the lengths of the two lists. So the only requirement is that if all of the elements of L1 are included in L2, then this function would return true, otherwise it would return false. So what this function is doing, that it is pattern matching on the two arguments L1 and L2. If the first is null, then regardless of the second, this is true, because null is always a subset or sublist of L2. And if L2 is null, then this should return false, because a non-null list cannot be a sublist of null, so it should return false. While in this case, when L1 has a head and has a tail, then this H, which is the first element of L1, is found in L2, and the result of this is combined or conjuncted with the rest of comparison of this tail of L1 with L2 using the same function. So here we have a recursive call to the same function. Let me compile the statement of this function, and then yes, it is okay. So the compiler accepts this function. So let me compute equality boolean list and prime, and we compare two lists where 5, 4, 3, 2, 1 is the first list, and the second list has elements but in different order, the same elements but in different order, 3, 2, 1. So this should return true, because all the elements of this list are included in this list. So this is L1, this is L2, so L1 is a subset of L2, so it should return true. Yes, it returns true. Remember that if we add an additional element, still it should return true, because all the elements of L1 are included in L2. Sorry, there is a type error, syntax error. Yes, it still returns true. Okay, so these two are actually this is different than equality on list, a Boolean equality of list, because it compares the two lists if all the elements of if the corresponding elements are the same, then the two lists are equal. But this is different. It says that if all the elements of first list are included in L2 in the second list, then we can say that this list L1 is inside the list L2, or it is a sub list of L2. In fact, the name of this function should be sublist L1 L2, or we can change it to a different name. Okay, so let me define a slightly different function to this equality boolean list n function, prime function. So let's find equality boolean list n, and there is no prime, so it's a variant of the function defined above. So it has two lists as the argument, net list, and it returns bool. Okay, so this is defined to be as using pattern matching. So first, this function is similar to the function we have just defined. The only difference is that in this function, the length of the two lists must be the same. The length of the two functions must be the same. So in pattern matching, we start with checking the length of the two lists. So length of L1 is compared with length of L2. And this is comparison. This match is compared with. So we have two possibilities. This is a Boolean function, so it will compare the length of L1 with the length of L2, and if they are the same, this will return true. And then if the list of the two are the same, the length of the two lists are the same, then we would call equality bool list n prime L1 and L2. So we are reusing this function if the lengths of the two lists are the same, and if they are different, then it should return false. And this is ended with dot. Okay, so it has error, syntax error, and the reason is that the spelling of the length is incorrect. Okay, so now it is accepting. Let me test this function and show you what is the difference between equality list n and equality list n prime. So equality list n. So these are the two lists where the length of the two lists is the same, and I compile it, so it should return true. And if I add an additional element to the second list, then it should return false. Why? The reason is that these two lists are not equal because there is an element 8 in the second list that is not in the first list. So this is equality on list, which compares if the two lists are of the same length, and if every element of this list is included in this list, then they can be called equivalent. So the name of this function is again a bit misleading, but this can be changed to equality boolean list or equivalence boolean unlist. So this would be different than the equality, where the order of the values or the order of the list is important, but here the order of the list or the members is not important. So if every element in the first list is included in the second list, then they are equivalent. But here not only that the elements should be included, but they should be in the same order. For example, the first element here is 5, the first element here should be 5, and so on and so forth for all the elements. And if this is true for all the elements, then the two lists will be equal. So a kind of that is equivalent function, and this is equivalence function. So we have defined a number of functions on netlist, and we will continue with lemmas and theorems on these definitions in next lecture. Thank you.